All right, it's not quite 9 o'clock, but I'll just go ahead and talk about the grades. So, sorry if this looks cluttered. This is all 3 exams that the class has taken. We started the class, at least according to my roster, with 26 students in here. So we've lost 6 students. So of the 26, only 20 students took exam 3. So what you see is only the data for those 20 students. For exam 1 is in blue, exam 2 is in orange, and then the gray is exam 3. You can see the trend here. Over the last 3 exams, the number of A's came down. Number of B's have kind of fluctuated. C's have gone up a little bit. D's have gone up. And then the F's have gone down. This kind of makes sense because we lost 6 people. So I'm guessing, well, no, those are the 20. So yeah, I don't know. Looks like we had more not passing exam 2. Averages, exam 1 average 89. Remember, I told you, exam 1 is like the one you want to start out good. The class did pretty well in the first exam. Very low standard deviation, which is good. And then these 2 exams have been pretty much the same in terms of averages. Our standard deviation has also been pretty similar on those 2 exams. Just means that the spread of the grades is about the same for exams 2 and 3. And then these are the actual students, each student that took the test. You can probably find yourself, like if you got a 99 on the first one, a 63 on the second one, a 77.5, you know who you are probably, right? So you can kind of figure out where you are here. The highest grade was 97.5. There were 2 of those, and then there's also this one. Just take that one out. So the low for students who actually took the exam, the low grade is 53.75. So yeah, that's it. I should have probably taken this one out because it's messing up the average. I think the average is a little higher if I take that one out. Let's see what happens. Where'd it go? Yeah, that's more realistic. There we go. So our average changed to a 70, almost a 76 on this exam. So, all right. Where did I put that thing? Did I delete it? There we go. Okay, if you have any questions about the exam, I have been known before to make mistakes while I'm grading an exam. So if you see anything on there that you're not sure why I took off, just please let me know, and we can talk about it. All right, but we'll do that on office hours. Anyone else want to pick up their exams? Yes, Chris.
Just real quick, do we have class on Wednesday?
Yes, well, it's not my choice. Okay. I could cancel class, but then I get in trouble if the department finds out. So I will be here. I do understand people do travel for the holidays and stuff. So if you're not going to be here, I will record the class. I'm not telling you don't be here, but I will be here. I will be lecturing. We're going to continue. But if you're not here, I'm not going to penalize you for it. All right. I'll record the class, but you know how technology can be. Sometimes shit happens and I can't control it, right? So if something goes wrong with my video, you know, that's just the way it is. Does that answer your question, Chris? All right, y'all ready? So I asked you last time that we met before the test, I asked that you please be ready to go today, so I don't have to sit here and rehash everything again. I know that because I watched the video. And in the video I said to please watch the video if you need to get up to speed. So this is what we ended with. We're in 8.2. We're talking about series. We're talking specifically about geometric series. And remember, this is just one type of series. If we get any series that ever looks like this, then there are 2 different scenarios that can happen. We either have convergence. If the absolute value of r is less than 1, we have convergence, and it will actually converge to this, which means we know the sum of the series. And then if the absolute value of r is greater than or equal to 1, we know we have divergence. And so I have some examples. We did one example in class, but I didn't do these. There's 4 more that I want to do here. And then we'll move on to the next topic. So the first one is just going to get us up to speed. The first example, if we're given this series 4 times 3 halves to the n minus 1. If you're given this series and asked, does this converge or diverge? And if it converges, what does it converge to? If you're asked that, then you have to recognize that this is a geometric series, right? And the way it's presented to you is, I mean, it's like right in front of you. It's exactly in this form. Do y'all see that? We have sum n equals 1 to infinity. We have a, right, a number sitting in front of something to the power n minus 1. So it's very easy to just look at that and see what a and r are, right? So for us here, this is geometric, right? We can say, okay, this is geometric. I know that a is 4 here, and r here is 3 halves. And so right away, I can just take the absolute value of r, the absolute value of 3 over 2, and that's bigger than 1, isn't it? And as soon as I know the absolute value of r is bigger than 1, I can conclude that this diverges. And I'm done, right? Very straightforward. Now, you're never going to see a problem like that on a test. This is just, again, to get you back up to speed of what a geometric series looks like. So we just did part A. Let's do part B. The only difference between part A and part B is that instead of 3 over 2, I flip it over and I make it 2/3 on the inside instead. So if I change this to 2/3, right? Again, it's in perfect geometric series form. A, r to the n minus 1. It's geometric. A is still 4, but now r is 2/3, right? And then the absolute value of that is less than 1 now, right? And now I know it converges, right? It converges. And not only do I know it converges, I know what it converges to. So I know what that sum adds up to be. It adds up to be a over 1 minus r. So a is 4 over 1 minus r. R is 2/3. So this is 4 over 1 minus 2/3 is 1/3. And then you can flip that up and you should just get 12. 4 divided by 1/3 is 12. Is this pretty straightforward? Yes? Okay, so let's see something more like what you're going to see on a test, right? Something like part C. By the way, we did D in class last time, all right? If you go back and look in your notes, we did D. While I'm writing this down, I hope you all remember that the drop date was last week, right? That's why I gave you that test and graded it, well, not right away, but I did it by Friday, in case you felt like you might want to drop the class. So you're all stuck with me now, right, at this point. So now that drop date's over, I just want everyone to know that, like, we will talk later about your grades. You know, if you have a test that's really low and the rest are okay, maybe we'll do something where the final can do something to help your grade come up. But let's cross that bridge a little later. Okay, let's get past the Thanksgiving holiday. We'll come back. We'll start talking about that. I guess what I'm saying is that if you're really concerned about one test grade hurting you, like, I will provide some sort of path for that not to be the end of it for you. But later we talk, all right? Okay, so now this right here is not in the perfect geometric series form right now because we don't have, well, the first thing I notice is we don't have n minus 1s, right? I don't have raised to the n minus 1, and you have to have that. Also, I don't see an a sitting, well, I guess there's a 1 here, right? You could say that's an a, but I've got 2 different numbers being raised to, n minus 2 and n plus 1. If this is ever going to be geometric, it's got to be 1 number raised to the n minus 1. That's it, 1 number to the n minus 1. So what I'm going to do right now is I'm going to try and see if there's a way that I can rewrite this where these are both to the n minus 1. I'm just going to use something that I've used in the past. I'm going to realize that there's a hidden 0. Right, hidden zeros are these really nice little, this nice little trick that we can do. Right there, where I have that n, I want a minus 1, right? I really want a minus 1 there. So what I'm going to do is I'm going to do -1, right? Because that's what I want. But I can't just -1, I have to +1 as well. So that's a 0, right? That's a hidden 0 right there. So I put -1, +1. But remember, I had a -2. So do you all agree that what I have written there is exactly the same as what I started with? It's just kind of written in a different way? And then that's all over, and I'm doing the same thing with the 7. 7 to the n, and I'm going to do -1, +1. Please don't confuse this with the completing the square. When we completed the square, we added a hidden 0, but we would do plus the number minus the number. It was always plus then minus with completing the square. When you're doing this, we actually want the -1, so I put -1 then +1, all right? Okay, good? Now, I know that the n-1 is what I want, so I'm just going to combine those two together, and then I'm going to combine those two together, and I'm going to rewrite this like this. Sum n equals 1 to infinity, -4 to the n-1 times -4 to the -1. So what I did there is I put these two together, I got a -1, and now I'm using properties of exponents that says that if I were to put this back together, right? If I were to put this back together, I would add these up, wouldn't I? I do n-1 minus 1, and that would take me back to where I was, n-2. Now, if you can get to this step in your head without having to write all this, great, okay? Great, you can do that. I'm just trying to show you what I'm doing, all right? Over, let's see, 7 to the n-1 times 7 what? Squared. Because I do 1 plus 1 is 2. Now, all of that was so that I could get n-1 powers. Now I see that both of these are to the n-1, right? Both of those are to the n-1. So I'm going to use this. I'm going to use this property from college algebra. It says that if you have some base to a power divided by some other base to the same power, you can create a fraction and just put that whole thing to the same power. I'm going to use that property right here. I have like x to the power, y to the power, so I'm going to put them together into a fraction. Let me continue here. So I have, what, -4 over 7 to the n-1? And then here, what I'm going to do, I'm going to take this -4 raised to the -1 really means I can drop it to the bottom, right? And it becomes a -4 on the bottom. And then the 7 squared is 49, isn't it? So I have a 1 on top, I have the 49 that was there, and then I drop that the -4 down like that. And I need to multiply. So this is just a number, isn't it? It's just a number. So what's 4 times, or -4 times 49? 196, right? -196. So we get, watch what I do here. I'm going to say this is equal to sum n equals 1 to infinity. I'll say -1 over 196, because this does become a negative on the bottom, right? I just decided to put the negative on top instead. And then times -4 over 7 to the n-1. Okay, I'm there. Because now I can clearly see this is my A, right? And then that right there is my R. And I'm raised to the n-1. This is a geometric series. So this is geometric. A is -1 over 196. And then R is -4 over 7. The absolute value of R is the absolute value of -4 over 7. Bigger than 1, less than 1? This is less than 1. So this series converges, right? It converges. So this converges. And what does it converge to? A over 1 minus R, right? So I'm going to write that down. I have that this sum equals A, -1 over 196 over 1 minus R. Be careful here, R was negative, right? So you have a double negative there, which will become a plus.
So I just want to make sure, so the absolute value is only when you're looking at R as less
Oh.
than, But you don't do it when you're actually setting it up.
Yeah, when you're doing it here, you leave it as whatever it is. But when you're checking for convergence or divergence with this test here, you always take the absolute value. Okay, and then we can figure out what that is, right? Should be able to. Let's see. Okay, we have negative 1 over 196 over 1 plus 4/7, which is 11/7. Weird. Okay, so negative 1 over 196 over 11 over 7, and then I can flip that up and make it 7 over 11 like this and multiply. And let me see, this is negative 1 over 77, I believe. Yeah, because 196, remember 196 was what? 7 squared times 4, wasn't it? Oh wait, I'm missing something, hold on. I canceled one of the 7s, so 7 times 4, 28 times 11. Sorry, that's not right. What's 77 times 4? 156? What? Oh, yeah, 28, sorry. What is it, 3 what? 308. Well, yeah, my math ain't working today. My arithmetic brain is not working today. Yes, your phone's wrong. Your calculator's wrong. I'm right, damn it. Okay, yes? Okay. That's it. Weird. Weird answer. Why is that adding up to be a negative number? This is an infinite sum, right? So let's go back and look at the sum. I just want us to make sure we understand what's happening here. Negative 4 to the n minus 2, right, over 7 to the n plus 1. Okay, let's just start seeing what this sum looks like. I mean, we're done with the problem. I just want to try and explain why we're getting a negative answer. If I let n be 1, let's see what we get. We get negative 4 to the 1, let's see, 1 take away 2, right, negative 1, over 7 to the, plug in 1 here, 7 squared, right? And then plus, now we let n be 2. We have negative 4 to the, 2 goes here, 0, over 7 to the third. Then minus negative 4 to the first over 7 to the fourth, right? That's what's happening? Okay, let's see what this number is right here. This is 1 over 7 squared times 4, negative 4 here. Negative 4, right? And that's what we get right there? And we did that earlier, right? That was negative 1 over 196. And then we're going to add to that, let's see what this is. 4 to the 0 is 1, right? 4 to the 0 is 1. So we get 1 over, and then 7 cubed, right? And then minus over here, sorry, that should have been a plus here, sorry. Plus there. Plus, and now this one's going to be a negative number, isn't it? Negative. So negative 4 over 7 to the fourth. And then I'll have a plus. The next number will be positive. The next number will be negative. Then positive, then negative, then positive, then negative. So what's happening here in the beginning is that this number right here is actually a pretty big negative number relative to this one. This is a really small positive number. And this is an even smaller negative number. And a smaller positive, then even smaller negative, then smaller positive. They're getting smaller. This one is actually kind of dominating the situation. This number in front is the one that's kind of bigger than all the other ones. And so even when you put all those together forever, right, you're going to wind up with a negative answer. Does that kind of make sense to you? Yeah?
Would it be that, like, usually since the first number is positive, that's why it always stays sort of positive?
Yeah, if this first one were positive, it would depend on how fast those went down. But in this case, with this geometric, the way this one, the fact that this was a 7, I think we can be pretty, 7 compared to the 4 up there, I think we can be pretty confident. But I wouldn't say it as a general rule. What's up?
Like, originally when you first broke it up, on that it's negative 4 to the n minus 2. Instead of doing plus 1 minus 1, can you just break it up like n minus 1 minus 1?
Yes. Yeah, that's what I was saying. If you don't need to go through that whole thing where you do the, add and subtract, or subtract and add the 1, you can just say, hey, yeah, I realize that that's the same as 4 to the n minus 1 times negative 4 to the minus 1. Without any, you don't need to show any steps for that. Okay, good? All right, so let's do the last example here.
So this one converges, right?
It converges, yes, it converges. All right, the last one is, and this is like really strange, 2.13434, and the 3,4 is repeating. And I'm asking us to rewrite that as a fraction. Rewrite this as a fraction or as a rational number. So look, little off topic but on topic. If you take all the numbers, right? Look at our number line. If you take all the numbers on our number line, all the numbers are made up of basically 2 groups of types of numbers. You have rational numbers and irrational numbers. All numbers in here fall into one of those 2 categories. The rational numbers are all the fractions, and the irrational numbers are things that are not fractions. So examples of, let's say examples of rational numbers. In other words, fractions. How about 1/4? That's a fraction, right? Written as a decimal, it's 0.25. 1/3 is a fraction. Written as a decimal, it's 0.33, what? 3 repeating, right? How about the number 5? Is that a decimal? Can you rewrite that? Well, is that a fraction? 5/1, yes. And that's written as 5, what, 0.0. Doesn't the 0 repeat forever? And just like up here with the 0.25, aren't there zeros here that repeat forever? Okay, a rational number is any number that when you write it as a decimal, it has a repeating pattern forever. Whether or not, it could be zeros forever, it could be 3s forever, right? All rational numbers, when you write them in their decimal form, will have some repeating pattern to them. Irrational numbers are things that don't do this. So irrational numbers are things like, and by the way, these could be negative as well. That doesn't change anything. The irrational are things like pi, right? Which is approximately 3.1415. And that goes on forever, but see, there's no pattern to it, right? No pattern. It just keeps going, but it never has any sort of pattern where you can put a bar over it. Other examples, E is about 2.718, and it keeps going. Square root of 2 is irrational, 1.414, . So these are all your irrational numbers, and these are all your rationals. Together put them, and you've got a solid number line, right? There's no gaps, no holes. So this problem right here is saying, hey, look, I'm giving you a rational number because there's a repeating pattern to it. Give me the fraction that gives you that number, because that has to be a fraction. I'm telling you, it has to be. Once you see how we do it, you'll understand, yeah, I could do that with any repeating decimal, and I could always come up with a fraction then, right? Okay. Side note, this was already a side note. A side note to this side note is that there are infinitely many of these, right? If you look at the number line, there's an infinite number of fractions. There are also an infinite number of irrationals as well. So it's not like there's only like 5 of these. Like there's an infinite number of these. In fact, in mathematics, there's 2 types of infinity, and you could say that there's more of these than those. But I don't want to go too far off onto that topic right now. So let's do this problem. So the first thing I'm going to do is I'm going to try and rewrite this as a fraction. I'm going to first rewrite this out in a different form, all right? So do you agree that this is the same as 2 plus, okay, do you remember on a decimal, the first decimal place is how many tenths you have? How many tenths you have? So that's 2 plus a tenth, plus the second decimal is how many hundredths you have? So plus 1 over 100 plus 3 over what? Oh, sorry. Wait, I said 1. I meant to say, put 3 here, right? 3 hundredths, sorry. And then what? 4 thousandths plus 3, where are we? 10 thousandths plus 4 hundred thousandths plus, and then that pattern would continue, wouldn't it? Yes? Now I'm going to go a little further. I'm going to talk about where I have the repeating. The repeating is at the 3, 4, right? This is not part of the repeating pattern. This is not part of the repeating pattern. So I'm just going to ignore this for right now. I'm going to ignore just for right now. I'm not going to pay attention to that. I'm just going to pay attention to the rest of it. And what I'm going to do is I'm going to see it's 3, 4, 3, 4, 3, 4, 3, 4, 3, 4, right? I'm going to put these two together with a common denominator. I want to put those two together with a common denominator. How would I do that? I'd multiply this one top and bottom by 10. So it'd become that, right? 30 over 1,000. Put those together, you get what? 34 over 1,000, right? Do y'all see what I'm doing? Put them together, you get 34 over 1,000. Then I'm going to put these two together. To get the same denominator, I have to add a 0 here and a 0 here. So what's that? 34 over 100,000. Five zeros, right? We had 3 zeros here, on the, 1 and then 3 zeros. Here we have 1 and we have 5 zeros. What would the next one be? 34 over 7 zeros, right? Plus, and then keep going. Follow? Okay, the whole point of that, is that right? The whole point of that is that this is starting to look like the part D that we did last class in terms of we can somehow turn this into a geometric series. I think what I'm going to do is I'm going to bring that 2 plus 1/10 back here just so I don't forget it's still part of this. And then I'm going to rewrite this as 34 over 1,000. I'm going to rewrite 1,000 as 10 cubed. And then I'm going to go 34 over 100,000, that's 10 to the 5th. And the next one would be 34 over 10 to the 7th. And doing it this way, I can keep going pretty easily, right? 10 to the what? 9th, right? You see the pattern, 34 over 10 to the 11th plus, and it keeps going. And I'm ignoring this right now, right? I'm ignoring that. I'm just working with this part right here. That part right there, I'm going to try and rewrite it in sigma notation. The part not in red, I'm going to try and write in sigma notation. So I'm going to say this is equal to 2 plus 1/10 plus, okay, now this sum. Sum n equals 1 to infinity. Okay, what do they all have in common? 34, right? That doesn't change. From term to term to term, it's 34. But they're all over 10 to a power, right? 10 to the 3, 5, 7, 9, 11. Those are your odd numbers starting with 3. How do we create a sequence of odd numbers starting with 3? 2n plus 2n? Did I hear 2n? They go up by 2 each time, right? So you need 2n plus 1. 2n plus 1, right? So I'm going to have down here 10 raised to the 2n plus 1. Do y'all see I'm just going back to a few classes ago when I was like, hey, could you create the sequence 3, 5, 7, 9, 11? And then we went around the room a little bit, right? 2n plus 1 will create that sequence. Questions? No? I need to see if I can make this geometric. I need to see if I can make that look like sum n equals 1 to infinity of AR to the n minus 1. That's what I'm going to try and do, all right? And what I think I'll do is I'll stop here and I'll come back to this. Let me just do that work over here. So this is some scratch work on the side. So I need to see if I can turn this sum n equals 1 to infinity of 34 over 10 to the 2n plus 1, if I can make it look like that. Well, the first thing hopefully you see is that that's not even close to n minus 1, is it? That's not even close to n minus 1. Right? So how in the world am I going to deal with that? Well, watch, okay? I have to show you these first times through these problems. It's all about me showing you what to do, and then you going, oh yeah, I guess I could have done that. Okay, is that true? Is that the same thing? The same, right? Same base, 10, 10. If you multiply those together, you'd add the exponents, you get 2n plus 1. What I'm trying to do is eventually get an n right here, an n, so that then I can do that minus 1 plus 1. So the first thing I did is split it apart. Now I'm going to do this, watch. Okay, all I did there, not much. I just moved that 10 with the 34 out front and then just rewrote this 10 to the 2n out here as a 1 over 10 to the 2n. The next thing I'm going to do, I'm not going to say this is tricky, but it's, I guess, not natural initially to think this way. Do you agree that this is true? Is that the same as this? Think so? Yeah, well, what happens when you have this back in college algebra, x over y to the n, that's the same as x to the n over y to the n, right? So if I have a fraction to a power, you apply the power to the top and bottom, right? Do you see that because this is a 1, if I do 1, that power on 1, what's 1 to any power? 1, right? So I'm using this, I'm actually just coming over here and I'm realizing that this 1 right here is really the same as 1 to the 2n because that's still 1 and now they're both to the same power, so I can write it like this. Still clear? One more step before we can, because I want to make this a minus 1 right here, right? N minus 1? Right now it's 2n. So I can't work with that. So I'm going to do this. 34 over 10. I'm going to rewrite this as 1/10 to the 2 to the n. And again, I'm going back to this property that x to the n to the m, if you have that in college algebra, that's still the same as x to the n times n. So if you multiply two things in the exponent, it's the same as taking it to a power then to a power. So that to a power, you multiply those two, you get this. I'm using that backwards. I'm realizing that this is 2 times n, and so I write it this way so that it looks like 1/10 to the 2, all that to the n. Do you all agree with that step?